Hey everyone, and welcome to the MAME podcast, the show where I interview interesting engineers, professors, and people I want to talk to. I'm Philippe, the VP Events of MAME, the McGill Association of Mechanical Engineers. And today, for the fourth podcast, I'm interviewing someone really interesting. May I introduce Alex Walsh? Hi.
Hello. Turn the video back on for the intro. Hopefully it lasts with the internet.
Yeah, exactly. So Alex has been having a bit of internet problems, so he's been a bit laggy. So he might turn off his video if it goes back again. But hi, Alex. How are you doing?
Doing very well. How are you?
I'm great. Actually, sorry. Should I call you Dr. Walsh?
No. Just call me Alex.
Okay, great. So I'll let you introduce yourself.
Yeah. So, my name's Alex Walsh. I did my Bachelor of Mechanical Engineering at McGill a few years ago. From there, I went and did a PhD in aerospace engineering, a master's PhD at aerospace engineering at the University of Michigan. And then I did a year postdoc in McGill doing some underwater research, underwater navigation. And then I moved out to California to work for a startup called Opener, and they do electric vertical takeoff and landing.
Cool.
And
so nice. Wow.
Back in Montreal.
Yeah. So you're resting. Are you from Montreal?
I'm from Montreal originally. Yes.
Yeah. So you're back home for COVID and fun times.
Yeah.
So you work for a drone company, am I right? So it's an electric drone, is that it? Or
so currently it's unmanned, but the idea is that it's that it will be manned. So I'm wrapping up work with them at the moment.
Okay.
I officially don't work for them anymore. I'm just doing a bit of contract work to tie up some loose ends and to keep my project going, just because it's important for the company. But they call it a personal aerial vehicle, but in Canada it will fall under the ultralight category. So it's an electric aircraft for a single person in the basic ultralight category.
Okay, so it's so it will eventually be controllable, right?
Right. So right now everything about it is unmanned and it's more or less autonomous. We do control it from the ground. Okay. And we send it commands, but let's say we have tests to set up. A lot of the tests will be pre-programmed. And so when the aircraft gets into the air, all you have to do is press run and then it'll execute the series of tests that you need.
Okay, cool.
Whether it is for stability, control, performance, safety, everything is just automated for testing. And it's a lot safer to do all the testing unmanned because you're not really putting anyone's lives at risk.
Right. And you're removing the variable that can change the most, I guess.
Yes.
So your specialty is with, if I'm not wrong, navigation and controls?
Yes. Yeah.
Okay. So
dynamic navigation control. Yeah.
So what exactly do you do for specifically you're programming the navigations?
That's exactly it.
Okay. Oh, cool.
So we have a bunch of sensors, and the question, navigation control, it can really be divided into three different sections, or
right.
Where am I, where should I be, and how do I get there?
Mm-hmm.
And each robotic problem has these same questions. So really I deal with is where am I? So if you take a bunch of sensors, how do you figure out the attitude, the position, the velocity to some accurate measure that the controller can then use that to either stabilize the aircraft or position it wherever you want to.
Right. And I imagine that's pretty, that has many applications. If you do it for drones, you can do it for underwater robots, as you mentioned.
Right. So I've worked on this for at the University of Michigan. I worked on this for spacecraft.
Mm-hmm.
That we small CubeSats that we launched. At McGill, I did some of the stuff for underwater applications. Yeah. And then now I'm doing it for aircraft. So the navigation problem, like the math is like very similar, and like a lot of the sensors are similar between them. Like there are a few like minor differences in sensors and how you deal with them. But, like a lot of it is very, very similar.
Wow,
Like what I focused on the PhD wasn't actually like estimation. It was more on the control side. So it's like, I don't know, you get to do both. It's fun.
yeah, exactly. And if you want to change at some point in your life, you have the skills to do that. And so that's pretty cool. So you started at McGill. So why did you choose McGill in particular?
I don't know, it just seemed like the thing to do. Yeah, no, it was a good school. I was trying to decide between a double honors in math and physics and a Bachelor of Mechanical Engineering. And then I just ended up choosing like I was at Dawson College. I spoke to a few people there, and then eventually I just ended up choosing mechanical engineering because it felt like something I could use more like right off the bat once I graduated.
Yeah, were you involved at all at McGill, or I think I saw on your LinkedIn page that you were involved with the Canadian engineering competition. Is that possible?
Yes, that was a good time. Yeah, I was VP hospitality for that.
Oh yeah, because McGill hosted it in when exactly?
2012.
12. Okay, cool.
2012. Yeah.
Were you on your last year?
No, I was on my second year. No.
Oh, okay, cool.
Second or third year? When did I start? I started in 2009. Or it was 2011 or 2012? 2011, possibly.
Okay.
I think I was my second year of engineering.
And you were VP hospitality, so for the
the Canadian engineering competition. Yeah, it was a really good time. Like,
cool.
My main responsibilities were making sure that all the students had a place to stay, and that they were well fed at all times, and that they had interesting activities to do at night.
I'm interested because I'm actually chair of MEC at McGill Engineering Competition. So we send out people to QEC, and then right now we're actually doing the online MEC. So it's
okay, that's
fun
interesting.
Challenge. Nice.
No, it's fun organizing stuff. Then I was a student president for the MIAE.
Oh yeah, cool.
I did that for like a year and a half at the end of my bachelor's.
Oh, nice. And that's for opportunities in aerospace engineering. So it's a plug to MIAE right there. I like it.
Yes. So I was student president of that for a year and a half, and then we did a student conference like with the MIAE and CREAC, which is like a research institute in Quebec for different research applications in Quebec.
Oh, cool. Yeah. Nice. And then you decided to go to grad school. Do you have any advice for that? Why did you decide to go there? And
I guess sure how this is gonna sound. So I did one internship at Bombardier, summer of 2012, and I don't know, like sitting in the chair of Bombardier, I could see someone who was like 5 years older than me, like next to me, and then someone 5 years older than them next to them, and then someone 5 years older next to them, and you could just see your like entire life in the rows in front of you.
Wow, yeah, I kind of relate. Yeah,
and it kind of like freaked me out just sitting there and just seeing, like, okay, once you do this, you just go there and there and there, and I don't know, it just didn't sit well with me, and I was like, okay, I can't do this. And I don't know, for me, some reason at the time, just thinking that if I got a bachelor's degree, this is what I would end up doing. And I didn't like that idea. And I wanted to go into more like space applications.
Right.
And because of that, I just didn't feel like a bachelor was enough for that. And so I wanted to at least do a master's.
Yeah. So the master's gives you the opportunity to maybe branch out and have more expertise.
Mm-hmm. Yeah, and only like now working in industry, like I can really see what tools you get at what level of education, especially when it comes to control.
Yeah.
So when people tackle a control problem, you're only given a certain number of tools during your undergrad, and you're maybe given a bit more tools during your master's, and then a bit more tools during your PhD.
Okay.
And so when you look at someone's solution to a problem and you see the route that they took, like right away, you can almost tell what level of education they have based off the tools they use to get to the solution.
Okay, cool.
Does that make sense?
Yeah, for sure. So the more,
so
to do grad school is maybe to have access to a bigger toolbox to solve problems, right?
I was gonna say that's exactly it. And honestly, like the tools that you get in your undergrad degree, like often like they're sufficient.
Yeah.
But like sometimes when you get to more advanced problems, it's like you just need the special tool and you don't have it. And so you have to like come up with hacks with like what you've got to like make it work.
Okay. And you figured that out when you were at Michigan and starting?
Honestly, I'm like, it hasn't hit me until like now that I'm in industry where I see people working. And sometimes all you need is, let's say, the tools from your undergrad, but it takes you like your master's and PhD to like solidify them, or like it takes more schooling or more training or just more experience in industry to solidify them. Like I don't know, there's like a saying where to learn anything you have to like learn it 7 times before you really understand the meat of it.
Yeah.
So sometimes like your undergraduate, like what you learn in undergrad is just so fundamentally important, but like it just doesn't sink in, or you can't make the links, or sometimes you can only apply it to problems that you see that are right in front of you, or problems from like you don't fully grasp of how to fully use tools unless you try to use them over and over and over again. And so maybe.
Yeah. And what's one thing that you work with like many times, say a year or regularly, that you learn at undergrad and you don't especially know that it's useful?
Differential equations, for starters. I like slept through that in my bachelor's and I have to relearn it like pretty quickly.
Yeah, I guess you use them a lot. Well, actually, you use them also in the other classes in the 3rd and 4th years. But yeah, so at Michigan for your master's, what was your topic of research? Did you actually have prior research experience when you started your master's?
Yes, so I did the honors program in the bachelor's at McGill. So I did research in dynamics of flexible telescopic robotic manipulators.
Oh, who's
so like
that with Professor Misra or?
No, I did it with Professor Forbes.
Oh, really? Oh, yeah. Actually, we talked about that, I think, in the podcast. Yeah. Cool. And that's where you met Professor Forbes?
Yeah. He was a brand new professor at McGill, and he was sending out this call for control of flexible robotic telescopic manipulators with like, so it's basically a robotic arm that's long and flexible and that can like extend, retract, and it's telescopic.
Okay.
And applications that he was citing were similar to the next generation Canadarm. And I was like, oh, space, that sounds really cool. Let's do that. So then I email him, and like, I guess one of my first questions was, what's control? I don't know what this topic is.
Were you
never heard of it before?
Or
I was.
How advanced were you?
I think 3rd year, beginning my 3rd year.
Okay, cool.
When I emailed him. It just sounded cool, so emailed him.
So Professor Forbes, for those who don't know, is on the first podcast, so go watch that. And he's teaching Mech 412, which is controls, basically. So so you worked with him on what task did you do? Was it how did it influence your move to Michigan or to grad school?
So my task was dynamics. So it was going through. It's essentially just dynamics. So deriving the dynamic equation, and it was doing a little bit of control on this robotic manipulator.
Okay, cool.
Coming out of, I guess there was research coming out of the University of Toronto that did a lot of how do you control the end effector of a flexible manipulator. And it's a challenging problem because oftentimes, let's say your actuators aren't co-located, so they aren't in the same spot as the tip of the manipulator. Like right, they're located at the joints. And then your sensors you might have sensors you might know the position at the end or at the tip. You might have sensors at the joints, or you might only know where the tip is, and you might not have sensors at the joint. And so it becomes a challenging problem, especially when you're like, if you want to control the tip, but your motors are at the joints, it becomes a more challenging problem just because your actuators aren't at the same place as where you actually want to control. And then add into the fact that it's flexible. So if you want to be able to control that robotic system, you first need a dynamic model.
Okay, yeah. And
so it's usually like, if you want to do control, you kind of have to do dynamics just because
right,
that's the name of the game.
It's pretty related. And then you moved to, why did you choose Michigan University? Or is it because of Professor Forbes? Because I think he moved there as well, no?
He did. I had applied to, I had a friend who applied to the University of Michigan, and I had never heard of it before. And he was doing a biostatistics. And so I never heard of it, looked it up, and turns out it's actually a very good aerospace school. And they have a wide range of control classes.
Oh yeah, okay.
Like they have tons of control classes. You could be taking control classes like every day for like 4 years and not be done with all of them. Like, it's a wide variety of control that they have, split between the aerospace department, the mechanical engineering department, electrical engineering department, and now they have a new robotics department sort of going on.
And
so
yeah, sorry, go ahead.
Yeah, so they have a lot of different offerings, and so Michigan was one of the schools I had applied to. And I didn't know Professor Forbes was going there at the time.
And were you involved with him in Michigan, or not at all?
Yes. So originally, due to funding, I wasn't going to go. But then Professor Forbes, he got a job as a professor at the University of Michigan, and then he told me that he needed a PhD student.
Oh, nice. He took you under his wing.
Long story short, that's how I ended up in Michigan.
And you were working on the same dynamics problems, or?
At first, I did a couple months to just wrap it up, but then it was on to new problems.
Okay, cool. And like what? Like the actually, you mentioned the underwater robots was later on at McGill, right?
Yes. So at Michigan, I did some extreme seeking control, which what that means is you have an objective function, and that you're trying to control your system to either minimize or maximize that objective function.
Right. Okay.
So, in one problem that we looked at, you had 2 fighter jets flying in formation, and you want to move the one that's trailing into a position that minimized its drag behind, or fuel consumption behind the second one. And so your objective function that you're minimizing is, well, you really want to minimize drag, but you sort of use a proxy because it's not like you can really measure drag, or it's it's very hard to measure. Another one that we looked at was if you have a satellite antenna or anything, and you want to maximize your signal reception, how do you turn it so that you maximize your signal reception?
Okay, cool. Wow.
That was another style of problem.
And did you know you wanted to do controls when you finished your undergrad, or you were still debating? Yeah, you were.
No, I knew I wanted to do control.
Okay, and what would you say to someone who maybe is debating and between controls and something else and isn't sure what he or she wants to do? Any advice?
Yeah, control is it's weird that control is not its own discipline, just because control you can apply it to every single discipline, whether you can go into healthcare and do control. like robotics in healthcare, insulin pumps it's like a control system running on that, keeping someone
Right.
alive. You have like people who do control in economics, people who do control in mechanical engineering, in aerospace, underwater. A huge part of autonomous cars is control.
Yeah, for sure.
The whole like AI and machine learning, when it comes to control, we typically just call that system ID. Like,
exactly.
And like this idea of like using neural nets like to accomplish things in control, like that's sort of like it's been around. It's like it's part of control. So it's like it's approaching these problems. Like a lot of times, let's say when you look at like machine learning, you might approach it from a computer science perspective, but like you can also approach it from a control perspective.
Yeah, for
and
sure.
So there's a lot of these different problems where like if you're in control, you can just tackle.
Yeah, it's like the backbone of any robotic machine that in any field, basically. That's what I think.
Right. And so like the aircraft that I'm working on, it's like it wouldn't do anything without like the people in control commanding everything to happen.
Yeah.
Like like the people who are in control, we're the ones who are like running the test or decide or a large part we're running the test or deciding the test. And so like we'll command the aircraft to do what we want, to do the test that we want, and we're driving this performance and specifications for the test. So yeah, it's like this neat position that you're in between like testing and also development, and like it feels like you have a lot of influence over like what the aircraft does. Or
yeah, exactly. And when you think about robotics and in general, you think maybe more the mechanical parts and the arms and everything mechanical, but a big part of robotics is the controls and navigation.
So, right. And for me, I just rather deal with the algorithm to make it move than to design a part that has to withstand certain loads or whatever.
Yeah, for sure. Do you feel like you have to be more creative, or is there a creative aspect to that, or no?
There 100% is a creative aspect to that, but I wouldn't say you need to be more creative. Like there's a lot of problems in like engineering design as well.
Yeah, for sure.
Like if I turn around and say, okay, like these ailerons aren't big enough because at low speeds, there's just not enough airflow to be able to create the torques I need. Right. Then it's like someone has to like go around, okay, can we fit a bigger control surface in? Like, how does it fit in the wing? How does it affect all these other parts? And it's almost like a puzzle that they have to, like both people have to solve together.
Yeah, definitely.
So, like, is it more creative? Like, I think each specialty like has its challenges, and you just have to remember that like, because I think like just because I prefer control doesn't mean that the other areas aren't equally as exciting.
Yeah, for sure.
Different people.
Yeah, definitely. And then, so if we continue your path, you did your. So my question is actually, is there a difference between master's and PhD in the States? I think there's a slight difference, or how does it work?
It varies from school to school.
Oh, okay.
Like different schools have different standards. I know, let's say MIT's master's is more like McGill's master's, where it's like a solid 2 years you're going at it. At the University of Michigan, you could, it was basically a list of courses you need to complete.
Okay.
And so people who finish their bachelor degree, like oftentimes they could just tack on a master's, like do an extra year, pay a few extra tens of thousands of dollars and get a master's. And for the PhD, it's if you're doing a PhD and you complete the required amount of courses, then you just send off an email and saying, well, I did these courses and they're like, okay, and then they send you the certificate.
Oh, wow. Nice.
So like the master's, like it changes from place to place.
Yeah. So at McGill, it's you take two years and then of classes, and then you're done. You get your master's.
Right, and at McGill, it could be like thesis based or non-thesis based. And if you're doing a thesis based master's at McGill, it's almost like a mini PhD.
Okay.
Or it's like a half a PhD at McGill. Whereas the master's at the University of Michigan, it's not like it's different.
It's
like they're called the same thing, but they're different.
okay. And I'm actually thinking about doing a master's, but I also want to do a minor. Do you think that's overkill to do a minor and a master's? And I don't know. What do you think?
So I found that the mentality towards education during, let's say, your undergraduate degree versus grad school are like, at least for me, it was very different.
Okay.
And I felt like the people around was also different. During the undergraduate degree, it was how can I finish these assignments as quickly as possible? Like maybe I did it wrong, I don't know. But my mentality was, okay, I need to get these assignments done. How do we get through these classes? How do we get good grades? Like,
right.
Like how do we get to the end?
Yeah.
Like unscathed. During grad school, the mentality completely changes to I'm here because I really want to learn this information. I need to learn this information because I'm interested in it, and I want to be able to take this information and apply it to these specific problems.
Okay. Yeah.
And I kind of wish I had that mentality during the undergraduate degree. Like, I'm not sure what it is about the undergrad, whether it's just like the environment around you, or there's just so many different tasks you have to attend to. It's hard to
concentrate on one or the other.
Concentrate on one. But during grad school, the mentality was like a lot different.
Okay.
At least for me anyway. I'm
yeah,
sure
I
like
that a lot. Yeah, for sure. In undergrad, sometimes you don't realize that you chose to come here to learn, and you get like overwhelmed really fast.
Yeah, and you're like, okay, I just need to like get these grades. I'm gonna fight for everything. I guess like
exactly. Yeah, that's you haven't done a minor, right? And you weren't on
no. But so getting back to that, grad school is way more about understanding and really enjoying what you're learning and seeing how you can apply it, or at least that's the way it was for me. So if you're interested in learning more, then by all means, absolutely go ahead and do that.
Okay, cool.
Like what are you, like what minor and what major are you interested in?
I'm actually thinking about computer science for a minor.
Mm-hmm. Yeah.
Because I feel like it's a useful tool to have, and maybe we don't do enough in mechanical engineering. So yeah, and then a master's, I'm not sure what I want to do it, what the topic would be, but as you said earlier, I kind of want to have more tools to figure out to solve these problems.
Mm-hmm.
So yeah.
Yeah, no, computer science is very useful, very relevant, especially these days. Like a lot of people who work with my team, or even people who aren't on my team, they need to be at least somewhat like coding literate.
Yeah.
And I find that it's like, maybe it's good to have like a class with just the basics of coding to get you started.
Mm-hmm.
But a lot of times you just need a problem that you have to solve and then try to use code to solve it.
Yeah.
It's hard. Like maybe that experience comes like outside of the classroom more than inside of the classroom. So oftentimes you just need a problem to solve and then solve it to learn code.
Yeah, you're right. And it's more motivating also.
Yes. So the question is like I know during our undergrad, it's like, okay, we wanted people to teach us code more, but now that like I've been learning, or now that I've been working with code a lot more, sometimes I wonder if it is worth having a dedicated class to do more advanced coding besides just the basics that give you the outline.
Right.
Uh,
Instead of actually putting yourself in the way of these problems that you can use coding to solve, right?
Yeah, because a lot of it you'll be doing it on your own anyway. To like sit there and code and solve, and like there's a lot of resources online for coding.
That's true.
It is good to have like the basics down pat and someone to tell you like, okay, this is what a pointer is, this is what like classes and methods are, and like it is good to have someone just to lay it out structurally for you and maybe give you like good principles of coding. But at the end of the day, you have to take the things that you learned in class and apply them to something.
Yeah, for sure.
And that's when you're gonna that's when you'll figure a lot of it out.
Yeah, that's good advice. So if we come back to your path after your PhD, you went to McGill. You went back to McGill to work on underwater. I'm interested in that. What did you do there or here?
So I did a lot of most of my PhD I did control, and then for the underwater stuff, it was navigation. It was SLAM, so simultaneous localization and mapping. So it's a problem where your underwater robot goes out into the ocean, into an unknown area, and it has to create a map of the area as well as figure out where it is inside that map.
Wow, that's cool. And sorry. Again, you worked on the programming of the navigation and using I don't know, do you use like radar or LiDAR or something like that to map the environment?
Yeah, so the company that we worked with, they have a underwater laser scanner.
Okay.
And the laser scanner would scan lines of the ocean floor. And then what we did is once you scan many lines of the ocean floor, you end up with let's say a submap of the ocean floor. And then when you lay out all those submaps and when you go over your path again, you'll have two overlapping submaps.
Okay, cool.
And then once you have the two overlapping submaps, since you're using a gyroscope and an accelerometer and another sensor to essentially predict where your path is, once you finally return to your original starting point, your prediction is going to drift. And so your two submaps aren't going to align with each other.
All right.
But hopefully you can recognize that these two maps are images of the same objects. And then based off the error of your two maps, then you'll correct your entire trajectory.
Wow, nice.
So get rid of any of the drift that you have, as well as to estimate any biases in your sensors and stuff.
And did you actually test the robots in the ocean or in a pool or something?
So at one point we did go out. It was more, we had all the sensors on a boat instead of an underwater robot, and then we drove the boat around to collect data to work on this project. And there's a few students who are working on this project. But
were you a student or you were a...
well, I was a postdoc, but there's a few other students.
Oh, yeah, okay. Yeah.
Who were working on this specific problem. And so I was just doing a small part.
And of all the projects that you've worked on, what's your favorite one or the most exciting one to you?
I think the most exciting one is the one at Opener, just because it's a 500-pound,
yeah, exactly.
I could say a drone, but you program it, you test it, and then you go out and then you see it working in real life.
Yeah, for sure.
To have that quick turnaround, and then you see the consequences of the design decisions that you make in front of you.
Yeah.
You might make decisions about either the algorithms that you have, the code structure that you have, and if you don't apply it to hardware, you might not get the full effect of the consequence of the decisions that you make. the decisions that you make while you're doing these design decisions or these engineering decisions, and then like they have real consequences, and then you can see it in front of you.
So are you, and in your, say when you're in a graduate school, it's more theoretical maybe, and
just the projects that I was working on, like space related stuff.
yeah, for sure.
It was more theoretical. Like I did have an opportunity to work with another professor in a satellite design lab, and so that was like I really enjoyed that because I was working with like a reaction wheel project. Reaction wheels. So in space, everything is like equal and opposite reaction for you to position your attitude. Like you can't have ailerons because there's no air. So what you end up doing is you spin a wheel in one direction and the spacecraft spins in the other direction.
Okay,
If you want to position yourself, you need at least 3 wheels for your degrees of freedom. And so to reorient yourself, you start spinning a wheel one way and the spacecraft will spin the other way.
Wow, that's cool. And you were working on the controls of the wheels?
Yeah, so it started with like how do you, like once you have the wheels, how do you design the circuits to make the wheel spin? And like, so I was like I was in way over my head.
Yeah, for sure.
I was like, I don't know what's going on. And then you're like looking at like you're looking at these spec sheets for these chips, and you're just like, you need pull-up resistors, bootstrap capacitors, like all these other terms, and then you read about like a small portion of the circuit. You're like, okay, I understand that, and then you move to the bigger portion of the circuit, and you're like, okay, now I'm lost.
Yeah.
But luckily, there were some very solid students in the electrical engineering department, like who knew some power electronics, and so then they were the ones who ended up designing the system, who ended up like speccing out and like drawing the circuit board, and then I was doing like the embedded programming of the chips to like other microcontrollers to actually read back the speed signals, and then to program, let's say, the voltages to get the motor to spin at the right speed.
Nice. And you know, in engineering, you can't know everything about these complex projects. You have to really choose what you want to work on, basically.
Right. Like I was like itching to understand and be able to like draw these things out, but like you only have so much time.
Yeah, exactly.
And so at this point, or at that point, I was like, I honestly, I just didn't have like the time to, you need other people. Like the time that it would take me to like understand and learn and figure everything out would have been like a substantial amount of time, and we just didn't have that. So it was great that there's other people there who had the expertise, who could like fill in and like work on these projects.
Yeah, definitely.
Yeah, you can't know everything.
Yeah, sadly. So do you have any advice for someone maybe who wants to work in controls and maybe drones? Do you have any advice, someone who's undergraduate? What can we do to maybe stand out? Or what projects can we work on?
Good question. Yeah, my undergraduate, I didn't touch hardware all that much during my undergraduate degree.
Okay.
During like the second year design project, I think McDonald was under construction, or the labs were under construction, so we couldn't touch that. I did an honors thesis that was more like on the theoretical side, and I only started touching hardware like in my later years of education. So I think having a good mix of like implementation, but also understanding what's going on is important.
So maybe be part of design teams or projects like that.
Yeah, I would say if you can get your hands dirty, that's a good thing. Because there are things that you learn while you're like implementing stuff that you just it would never occur to you otherwise, or you hear about things and then it doesn't actually make sense until you see it in front of you in real life.
Yeah, for sure.
So whether it be a design team, whether it be doing something on your own just for fun, like, I don't know, if you're into photography, like build yourself an azimuth elevation mount to make your camera like move automatically or something. That will teach you how to like 3D print stuff. You'll get a Raspberry Pi or an Arduino, like some motors. You'll be able to solder stuff easily together, and like you'll just end up learning. You'll end up learning something, something along the way, and then at that point you'll like learn coding. You'll need to know about sensors. You'll have to learn about feedback loops. Like,
and if you
just find something you're
really
interested in,
right?
Yeah. Like at one point during my PhD, I just bought like these make fun like electronics projects to like solder, just to learn how to solder things and like make lights go on and off. Like it was very basic. Like it was the kind of stuff that you see like in elementary schools or high schools that kids are playing around with, and there I'm like in the middle of my PhD, like for fun on the weekends, like reading the same books, because I mean you
have to learn it at some point.
Like doesn't matter when you learn it, like no ego. Like if you don't know, you don't know it. Like
yeah, exactly.
Nothing to be embarrassed about, and you just start at the beginning and have fun with it.
yeah, for sure. So yeah, do you think people should start learning maybe programming earlier on in high school? Maybe I think some schools have started learning programming. I think that might be a good thing, especially in the world we live in, where computers are everywhere.
Programming is, I mean, I know there's more than one language, but it's like a literacy. Like, are you programming literate? And even if you learn one language, like a lot of the things that you learn will carry over into like other languages that you pick up.
Yeah.
And so I do think it is important, and like there's like important ideas that you can learn. And there's just like like I don't consider myself a software engineer. Like I use code and I program, but like I don't know, I compare it to like English. So not everyone who writes English is a poet. Like there are a lot of people who use English and who write English, and like they could be lawyers, they could be academics writing papers, they could be journalists, there's like a lot of different people who who write or who produce written documents. But just because you code doesn't mean
you're a programmer.
Doesn't mean you're like a full-on like software engineer or computer engineer, but you still need to have, like when you pick up a document and read it, you still expect like full sentences.
Exactly.
And like a certain you expect to have like a certain amount that you can read, and expect certain standards. And so I think the same thing with code is that writing good code is like, it's definitely a skill to have. And sure, you might not be like programming like an operating system, but you're still writing something for yourself. And when you come back to it in 5 years, you want to be able to look at it and understand what you did and what's going on.
Yeah.
And so that's like a really big point, and you want other people to understand what you wrote as well.
For sure. Yeah, I completely agree. Well, it's been fun talking to you, Alex. Thanks for coming on and talking to me. And so, what's
my
next?
Pleasure.
Do you have any projects or ambitions, maybe?
The future, yeah. Honestly, I don't know what's going to happen in the future.
So it's exciting then.
Yeah, I'm gonna try to find work.
Are you trying to come
in Montreal?
Yeah.
Yes. So I'm gonna be looking to find my next project in the Montreal area.
Cool.
It's good to be back. I moved like, I don't know, 4 times in the last 4 years and like 7 times in the last 8 years or something. I don't know. A lot of hopping around, and so I'm excited to be in one spot.
Thanks a lot for coming on.
Pleasure.
And hopefully I didn't take up too much of your time.
Yeah, no problem.
So thanks a lot, and have a great day.
Thanks, you too. Take care.